Solving and graphing multi-step linear inequalities really isn't that much more difficult than the previous lesson. They just add in one more step. So if I'm looking at 2/3 x plus 3 is greater than or equal to 11, I'm hoping by now it's pretty obvious that the first thing you want to do to both sides of this inequality is to subtract 3. When we do that, we're left with 2/3 x is greater than or equal to 11 minus 3, which is 8. Now, we've got a fraction times a variable, and to get rid of that, we multiply by the reciprocal of the fraction, which in this case is 3 over 2. I can cross-cancel here. 2 goes into 8 4 times, and I'm left with x is greater than or equal to 12. Now I want to reference what I said earlier about the number one most common mistake kids make when they're solving inequalities, and that is that they forget to flip the inequality whenever I multiply or divide by a negative. In this case, we multiplied by 3/2. 3/2 isn't negative, so we don't have to flip the inequality. The other thing I want to mention is the fact that this inequality can be read in both directions. You can read it as x is greater than or equal to 12, or you can go from right to left and read it as 12 is less than or equal to x. Logically, they mean exactly the same thing. In creating the graph for this inequality, we draw a number line representing the x-axis. Again, I do want to know where 0 is as a point of reference. 12 is our boundary. So that's the only hash mark I'm really going to make. Now, some teachers will ask you to make every hash mark between 0 and 12. I see that as the first sign of a misspent youth, but that's just me. I'm going to put a circle around the 12. And because our inequality is greater than or equal to, I have to shade in that circle. The reason being that 12 is a viable solution for x. 12 is greater than or equal to itself, to 12. So it will work in this inequality. My next responsibility is to shade the correct side of this boundary. And we want all the x's that are greater than or equal to 12. So those are numbers like 13 and 14 and 15 and 800 million. And they all exist on the right-hand side of 12. I shade to the right. I make an arrow indicating that it goes on forever. And I'm finished. The next one has I don't know, a little bit more sophistication, if you will, but it's not really any harder. The only thing that's different about this inequality is I have to distribute my negative 2. When I do, I have negative 2x minus 6 is less than 4x minus 7. Now, I choose to add 2x to both sides of this inequality. I could subtract 4x. Actually, you know what? I will do it that way. So I'll subtract 4x from both sides of the inequality. I have to stress it doesn't matter whether I subtract 4x or I add 2x. I'll end up with the same answer in the end anyway. Negative 2x minus 4x is negative 6x. Minus 6 is strictly less than negative 7. I'm going to add 6 to both sides of this inequality. That leaves me with negative 6x is strictly less than negative 7 plus 6 is negative 1. I need to move my paper down a bit. Extend the page. And now I'm going to divide by negative 6. As soon as I do, I have to flip that inequality because I've just divided by a negative number. So x now is greater than positive 1/6. I create a number line indicating the x-axis. I do want to know where 0 is. 1/6 would be to the right of 0. I put a circle around it because it's my boundary. This time I'm not going to close that circle in. And the reason is that 1/6 is not a solution of this inequality. 1/6 is not greater than 1/6. If this said greater than or equal to, I'd be okay and I could shade it in, but that's not the case. And then I ask myself, what numbers are greater than 1/6? Well, they're numbers like 1 and 2 and 17 and 800,000, and they all exist to the right of 1/6 on the number line. You simply shade that in that direction, put an arrow, and this is how you solve multi-step inequalities. Please remember, whenever you multiply or divide by a negative, you have to flip that inequality.